In this unit, we're going to be examining linear equations in two variables. So the question is, what is a linear equation in two variables, and under what circumstances do we find them? That is, what sort of situations give us a linear model, a linear equation, as our description of the situation. Let's start with what is a linear equation. The simplest condition is only the first power of any variable appears. And then the other two are just getting a little bit more specific. Variables are never multiplied by one another, so not only do we not multiply a variable by itself, we never multiply it by another variable, and variables never appear in denominators of fractions. So, just to see some examples, the equation x plus y equals 5 would be linear. Y equals 3x minus 4, linear. 2x minus 1/3 y equals x plus 2y, linear. Notice that this is the number 1/3 multiplied by y. If this were 1 over 3 times y, this would be completely different. In fact, 1 over 3y equals x would be an example of an equation that is not linear. X squared plus 2x minus 4 equals y, not linear. X plus x times y plus y equals 2, not linear. Notice the variables can appear on the same side of the equation, they can appear on opposite sides of the equation. We can even have each variable appearing on both sides of the equation. This word linear doesn't tell us anything about where the variables appear, just what powers appear, and the fact that all that ever happens to a variable is being multiplied by a number, and then addition and subtraction. Now, this word linear suggests something about these equations, and in fact that suggestion is correct. If an equation in two variables is linear, its graph is a line. Let's see an example of that. Here we see the graph of the equation x plus 2y equals 6. Now we'll see later on how I came up with this graph. But for now, what I want you to focus on is, what does it mean when we say that this is the graph of this equation? Well, we mean that every point on this line is a pair, x, y, so that if I take x and add it to 2y, I get 6. That works for nice points on the line, like this one, for example. This point is x is 2, y is 2. And in fact, if we take 2 plus 2 times 2, we get 6. It works for slightly less nice points, like this one. Here we see x is 5, y is, well, this is halfway between 0 and 1, maybe 1/2. Again, if we take 5 plus 2 times 1/2, 2 times 1/2 is 1, we get 6. It even works for really kind of awful points on this line that are hard to read, like, oh, that point. That point looks like it might be x is 2/3, y is 2 2/3. Does that work? 2/3 plus 2 times 2 2/3. That'll be 2/3 plus 4 4/3. This isn't a actual mixed number, but we can do this arithmetic in our head. 4/3 plus 2/3, that's 6/3. which is 2, right? So 4 and 2, that's 6. If you weren't happy about that arithmetic, you could also ask a calculator to work that out for you. But yeah, even for unpleasant points on this line, if we plug the coordinates of the point into this equation, it really does work out. So when we say this is the graph of our equation, that's what we mean. We mean every point on this line is a pair that works in this equation. Okay, so linear equations are really nice then, right? Are they useful? When do they come up? A linear equation is the correct model for situations where, as one quantity changes, the other changes at a constant rate. Now we're going to see several examples of this coming up right here. But just to illustrate this explanation, I'm going to give you a simple example right now. Suppose that a hotel room can hold 5 people, either adults or children. Write an equation relating A, the number of adults in the room, and C, the number of children in the room. So before we even start to write our equation, I want to call your attention to a couple of things. The first is that we are not calling our variables x and y. We're giving them names that relate to what they represent. A represents the number of adults. C represents the number of children. This is a really good practice when you are modeling a situation, just so that you can look at your model and know what it is. The second thing I want to call your attention to is this word, relating. The equation we're about to write gives a relationship between the two quantities that we're interested in. There will be times when I say, what's the relationship between A and C? And what I'm looking for is the equation that describes the relationship. Now the last thing I want to call your attention to is, even though the names that we gave them reflect what they are, we have written down in a place that it's easy to refer back to them what each variable represents. This is also a very good practice. When you're solving a long, involved problem, it's really easy to forget what you're doing. So let's write down this equation now. Well, our hotel room can hold 5 people altogether. How many people are in the room? If we take the number of adults plus the number of children, right? Everyone in the room is either an adult or a child. We add them together and we get the number of people in the room. It can hold 5. So the number of adults the room can hold plus the number of children the room can hold is 5. Notice that this equation is linear. Only the first power of any variable appears. We never multiply variables. We never divide by a variable. Is it the case that as A changes, C changes at a constant rate? Well, yeah, for every adult we add into the room, we have to take a child out, don't we? So this equation, A plus C equals 5, describes this relationship between the variables A and C. This is a linear model because if we change one variable, the other one changes at a constant rate. Its equation is a linear equation.